L'Hopital's rule. L'Hopital's rule has to do with limits and a way you can do certain kind of limits a little quicker and easier than before. So for one thing, it will help us do some limits we did before in a simpler way, but it'll also allow us to solve some limits that we couldn't have otherwise. Um, so let's consider, for example, this limit. The limit as x approaches 0 of e to the 2x minus 1 over x. Nothing we've learned so far in calculus would teach us how to solve that by hand, just using algebra methods. We can do it in the calculator. If you remember, we can solve limits in the calculator by plugging them into y equals. And we get, let's see, e to the 2x minus 1 over x. And if we go to the table, remember we can plug in whatever we want. Give me just a second. Sorry, I thought that was going to clear it out. There we go. Okay. So we can plug in whatever we want. We want to find the limit as x approaches 0. So we can solve this by doing 0.1, 0.01, 0.001, and so on. Alright, it appears from that side anyway we're approaching 2. So now let's do it from the other side. Negative 0.1, negative 0.01, negative 0.001, and so on. Okay, so it does look like from both sides we're approaching 2. So we would assume the limit is 2. And it is. But the question is, what if we don't have a calculator? We need to know how to do it without. And that's where L'Hopital's rule comes in. So here's what L'Hopital's rule says. If you have the limit as x approaches c of f of x over g of x, then that is going to be equal to the limit as x approaches c of f prime of x over g prime of x, assuming, and this is important, assuming that f of c over g of c is equal to 0 over 0 or infinity over infinity. So those are called indeterminate forms when you have 0 over 0 or infinity over infinity. And if you end up with that, then you know you can use L'Hopital. But it's important to make sure you do have one of those forms before applying L'Hopital, because that's the only time you are allowed to use L'Hopital. So for example, if I plug in 0 up here, if I plug in 0 for x, that's e to the 0, which is 1. 1 minus 1 is 0, so it is 0 on top. You plug 0 into x on the bottom, and it's 0 on the bottom. So 0 over 0. This is an indeterminate form. Now here's what L'Hopital allows you to do. You can take the derivative of the top and the derivative of the bottom, and be guaranteed that if you take the limit of this new function, it's going to be the same as the limit of your old function. So let's plug in 0 now, and we get 2 times e to the 0, which is just 2. We get 2 over 1, so our answer is 2. So L'Hopital is allowing us to use derivatives to better take our limits. Here's an example of one we could have done earlier with the dividing out method. So we could have factored the bottom, canceled out the terms that were in common, and then plugged in the 3. But let's do it with L'Hopital this time. Now if you notice, if we plug in 3, that would give us 0 in the top and 0 in the bottom. So 0 over 0 is one of those indeterminate forms, and it will allow us to use L'Hopital. So if I take the derivative of the top, it's just 2. The derivative of the bottom is 2x. Now if I plug 3 in for the x, I get 2 over 6, which is 1/3. That's how simple it is with L'Hopital. Let's take the derivative of the top, the derivative of the bottom, plug in your number. Okay, this one. Let's just quickly remind ourselves about the limits for infinity. Infinity, if it is bigger on top, it goes toward infinity. If it's bigger on the bottom, it goes towards 0. If they are going at the same rate, then you need to look at the coefficients and go with those. Now, natural log is very slow. Natural log is the slowest pretty much function we have. So natural log is going to move more slowly than the x on the bottom. In fact, let me just illustrate this for you really quickly. Let's put y equals natural log of x in, and let's put x in and compare how they grow. So let's just look at like 10, 100, 1,000. We'll delete the rest so it doesn't distract us. Let's try 1,000. There we go. Okay, so if you notice, obviously x is just going to do the same thing. So when x is 10, x is 10. When x is 100, x is 100, and so on. But when x is 10, natural log of x is 2.3. When x is 100, natural log is only 4.6. When x is 1,000, natural log is only up at 6.9. So just imagine this for a second. You're looking at a graph. We usually just look at the window from 0 to 10. If you were to look all the way out to x equals 1,000, natural log would have only risen up to 6.9. That's how slow this function is. So natural log is pretty much the slowest thing there is. So since we've got something slow on top, something faster on the bottom, this would mean that we're going toward 0. Now, you may be able to look at that and tell, but to guarantee it, we need to consider L'Hopital. So for example, natural log of x. It does go to infinity. It keeps raising. It keeps going up and up, even though it does so slowly. X also goes up and up, obviously, because x is approaching infinity. So we get an indeterminate form, infinity over infinity, which means we are allowed to use L'Hopital. So we take the derivative of the top over derivative of the bottom. And if you simplify that, it's just 1 over x. Now you can see, obviously, the top is just 1, the bottom is going to infinity, so our limit would be 0, just as we suspected. Okay, now this time we're doing the limit as x goes to negative infinity. Alright, well if you plug big negative numbers into x squared, it's still going to infinity because it's getting huge, because that squared is changing the negatives back to positives. And negative infinity into e to the negative x is also going to infinity, because the negatives will cancel out, so you're getting very big numbers. So we are allowed to apply L'Hopital. So we take the derivative of the top and the derivative of the bottom. Okay, so now the top is going to negative infinity. Think about it, 2x, then you go to negative infinity, it's just getting very big negative numbers. And the bottom is also going to negative infinity, so that's an indeterminate form, again. So you are allowed, if you get an indeterminate form again, to use L'Hopital again. So I'm going to take the derivative one more time, which gives me this. Now the top is not moving, it's just equal to 2, period, while the bottom is going toward infinity. So if the top's staying the same, bottom's going toward infinity, we know the limit is going to be 0. Now this one's different. This one you see is different. It says e to the negative x square root of x. This isn't a fraction, but we can rewrite it as a fraction. So that's what I would suggest you do first. Because if you bring e to the negative x down to the bottom, it'll just become e to the positive x. Now, our top is going to infinity. You make x bigger and bigger. X to the 1/2 does go to infinity. And our bottom is also going to infinity. So we can apply L'Hopital. We take the derivative. We get this. Now before you try plugging in infinity, I would rewrite this. Most of the time you don't want negative exponents. So let's move this to the bottom and make it 1 over 2x to the 1/2 e to the x. So we just move the 2 from the 1/2 to the bottom, move the x to the negative 1/2 to the bottom, made x to the positive 1/2. So now the top is 1 and the bottom is going to infinity. So again, the limit's just going to be 0. Okay, here's our last example. The limit as x approaches 0 from the right of x cubed over x cubed times cotangent x. Again, not a fraction, but we can change it to 1 because cotangent x is the same thing as 1 over tangent x. So I can just rewrite it that way. Now, if I plug 0 in the top, I get 0. If I plug 0 in the bottom, I get 0. So let's take the derivative and see what we get. 3x squared over secant squared x. Now, secant of 0 is 1. So secant squared would just be 1 squared, which is 1. So we end up with 0 over 1 when we plug in the 0, and we get 0 as our answer. I know a lot of these examples were 0. That is common to get 0, but don't think that it's going to happen all the time. If you need practice with these, look at page 537 in our books, and you'll find the examples there.